All right, everybody, welcome back. So let's do some examples with Green's theorem. We've got a couple of fun ones here today. So let's let C first be the unit circle in the plane centered at the origin. We love this one, right? And let's let big F be the vector field on the plane given by arctangent of x in the first component and x squared plus 7 to the y in the second component. What the heck is going on with this vector field, right? These functions, oh no, I don't know if I want to deal with these functions. Well, I don't know. Yeah, I wouldn't know if I want to actually integrate using or do a line integral of f along c from sort of like first principles here. So maybe we could try Green's theorem instead. So notice that the second function q of xy is x squared plus 7 to the y. The partial derivative of that function with respect to x is just 2x, which I like a lot better. That removes this funny exponential function. I love that going away. And similarly, arctan of x, that's p of xy, its partial derivative with respect to y is 0. So that makes arctan of x go away too. So that's very nice. So really that difference in question then is just 2x, which seems much easier to integrate over the unit disk in the plane, right? If we have the unit circle here, it bounds the unit disk. And we know how to do integrals over the unit disk, right? We can just use polar coordinates. We love those now. So we'll have D, the region enclosed by the unit circle, is the set of r theta such that r goes between 0 and 1, and theta goes between 0 and 2 pi. Great. So then Green's theorem says that we can trade the line integral along f of c for the integral of 2x along this disk. But how do we do that? Well, we'll replace 2x with 2 times r cosine of theta. That's what x stands for in polar coordinates. And don't forget to multiply by the polar coordinate Jacobian matrix determinant r, right? Ooh, gets you every time. Okay. And so we'll really integrate the expression 2r squared cosine theta as r goes from 0 to 1 and theta goes from 0 to 2 pi. So the first of those gives us just 2/3 times cosine of theta. And then we integrate that, we get 2/3 times what? Sine of theta. So evaluating at 2 pi and at 0 gives us that, each one of these values is itself 0, so the difference is 0. And so this product is 0. And so this line integral is 0. Very nice. Now, notice that this vector field is not conservative. Well, we didn't really say that here, but let's go back and see if we can see that it's not conservative. Let's see. Oh, right, it's not conservative because this difference is not 0, right? We would need that from what we had discussed before. So this vector field is not conservative, but along this one specific closed loop, it does line integrate to 0. So don't get fooled by that. It's only the case that you have, like, we can only use that, that implication in the other direction. We can only definitively say, using an integral, that our vector field is not conservative if we exhibit a closed curve along which that vector field integrates to not 0. But just having one particular closed curve where it integrates to 0 could just be a coincidence. So don't get fooled by that. Okay. So then this next example is kind of fits in part of a more general application that I really love of this theorem. So we can use it in the opposite direction and trade a double integral over a region D for some line integral of a vector field, where we do a line integral over the boundary of the region D. This is rather clever. And we might like to do this in the case that this function dq dx minus dp dy is maybe some particularly nice function. In fact, we might even like to manufacture or engineer our vector field so that we can integrate and have a function here that is maybe very nice and can get us an integral that has some kind of geometric meaning. namely that maybe computes some area for us. So this is a sort of clever trick that if we can select a vector field, P and Q, whose difference here, the partial derivative of Q with respect to X minus the partial derivative of P with respect to Y equals to 1, then that line integral over the boundary of P dx plus Q dy will compute by Green's theorem the double integral over d of the constant function 1 on d, but we know that that is the area of d. So we can compute the area by doing this line integral. Very clever. So let's see an example of one of those. Here's some examples of some choice vector fields, big F, that satisfy this property that the partial derivative of Q with respect to X minus the partial derivative of P with respect to Y equals to 1. One choice is to have 0 in the first component and X in the second component. Another possible choice would be to have minus Y in the first component and 0 in the second component. And still one other choice would be to have minus Y over 2 in the first component and X over 2 in the second component. And these are not the only choices of big F, but these are some popular ones. So I think in the next example, we'll probably pick one of these first two just because they're kind of clever and convenient. So if you're asked to compute the area of some region of the plane that has a nice boundary curve, you might choose to use this Green's theorem approach instead and do a line integral. And then you are free to choose the vector field just so that it satisfies this equation that I'm circling my mouse over here. So let's do it. So we'll use Green's theorem now to compute the area that's enclosed by an ellipse, whose equation is given to us in rectangular coordinates by this guy. It's x squared divided by 9 plus y squared divided by 25 equals to 1. So this is an ellipse that opens out like 3 in the x direction and 5 in the y direction. Okay? And we could find a way to compute this using a double integral. I don't think it would be too hard. We could probably even use like a calculus 2, just single variable integral. But let's try to use this theorem today just to kind of demonstrate another one of its sort of unsung powers. Well, I guess these aren't unsung powers. They're definitely well known. In fact, there's even a whole device that kind of operates off some of the same principles, although I believe it predates the sort of formal statement and discovery of Green's theorem. And I'll talk about that a little bit more when we get to the end of this example. So let's parameterize this ellipse. It's kind of like the unit circle that's centered at the origin, except it's been rescaled in the x direction by 3, and it's been rescaled in the y direction by 5. So we can use that same standard parameterization of the unit circle in the xy plane, but just rescale the x component by 3 and rescale the y component by 5. I think this is really a clever trick to remember in terms of parameterizing things like ellipses. And I know it's something that should probably be a little bit awkward for y'all at this stage in your mathematical life, thinking, how do I come up with this parameterization? Well, I don't know, just come talk to me and we'll get some more practice and maybe set you on the right path to get some more practice. And as it looks here, we go all the way around this ellipse. So t goes from 0 to 2 pi. Okay? And so let's compute the area enclosed by this ellipse. We will consider the vector field whose first component is 0 and whose second component is x, as this vector field satisfies this nice equation, namely that its partial derivative of q with respect to x minus partial derivative of p with respect to y equals the constant function 1, which is the function that we must integrate in order to compute the area of the region in question. And so I said here again, you're free to choose another vector field, and some may work nicer than others, so experiment. It looks like there's a lot of experimenting going on here between parameterizing curves and picking sort of choice vector fields that satisfy this equation. There's a lot of room for freedom, and there's probably a lot of room for mistakes too. So be careful. I don't know. Okay, so we'll let D denote the region that's enclosed by that ellipse, the one whose area we'd like to compute. And so Green's theorem says, well, really, Green's theorem doesn't apply until the second equation here, but the area of D we know will be the integral over D of the constant function 1. And then Green's theorem says that that is in fact equal to the line integral of the vector field F over the ellipse boundary curve C. So let's compute that line integral. So let's see. Recall, how do you compute a line integral? Oh my gosh. Well, recall, we'll trade it for the ordinary single variable integral from 0 to 2 pi, the two parameter bounds of the single valued function now that's given to us by the dot product of the vector field evaluated along our curve dot producted with the tangent vectors to that curve. Okay, so this dot product gives us a single number for each t. So this is now a single valued or scalar valued function of t. We're going to integrate with respect to t from 0 to 2 pi. So let's compute each one of these vectors so that we can get these dot product and get off the ground here. So the tangent vectors to the ellipse, given the parameterization we had, would be r prime of t is minus 3 sine of t in the first component and 5 cosine of t in the second component. And f of r of t, well, remember, in the first component, f was 0, and in the second component, f was x. And x of t, coming from the function little r, was 3 cosine of t. So that will be in the second component of f of r of t. Okay, so then if we take this dot product here, what do we get? We get 0 times minus 3 sine of t, well, that's 0, plus 3 times 5 times cosine squared of t. So that is 15 cosine squared of t. So let's integrate now that function as t goes from 0 to 2 pi. We'll invoke the half angle identity here, and we'll have the integral of 15 over 2 times the quantity 1 plus cosine of 2t. And that becomes 15 over 2 times t plus 1/2 sine of 2t, which we can then evaluate at t equals 2 pi and t equals 0 and take the difference. Notice that sine of 4 pi is 0 and sine of 0 is also 0. So we're left here with just 15 over 2 times 2 pi, which is 15 pi. Notice, I mean, I don't think that's a coincidence there that we had the sort of, we had the unit circle sort of warped in the x direction by 3 and in the y direction by 5, and then, oh my gosh, this area becomes 15 pi instead of pi that was the area of the unit circle, right? So that's all for this example, and I guess one more thing I will say that I kind of referenced earlier in this video and want to follow up on is that there's a fun thing that you can look up on the internet, maybe Wikipedia or something like that. It's a tool called a planimeter. That's Planimeter, I believe is how it's spelled. And it's this fun, cool tool from sort of, I guess, engineering land or something. So it might be of interest to some of you who study that kind of thing, that you can trace this little tool. It has a little wheel on it, and you can trace it around some curve in the plane, and it will compute for you up to maybe some decimal approximation the area of the space enclosed by the curve that you traced around. And so the mechanism behind the planimeter has some relation to Green's theorem here, although I believe the device itself actually predated the formal statement of the theorem. So that's some interesting history there. Maybe you can learn more about that and tell me, because I've never had need to actually use a planimeter before in my life. But I do love Green's theorem. So that's fun. Let's see. So stick around for next time. We're going to maybe tackle a completely different topic. We're going to leave the land of curves in space and curves in the plane and get a little bit stronger, maybe a lot bit stronger, and talk about surfaces in space and how to parameterize them in a way like we did with curves, using just maybe 2 coordinates to parameterize a 2-dimensional surface. Don't miss that. It's going to be really long and scary. So we'll see you then.